show that the function f of x equals 15 minus 2x minus x cubed has exactly one real root, and find the interval of consecutive integers that it lies within. The first thing to do is to determine whether the condition is met for the intermediate value theorem to apply. The function f of x, which is 15 minus 2x minus x cubed, needs to be continuous on the closed interval that contains the root. Now we do not know yet what the closed interval that contains the root is, but 15 minus 2x minus x cubed is a polynomial. And a polynomial is continuous on any interval. And therefore, it will be continuous on the closed interval that contains the root. So the condition is met, and the intermediate value theorem does apply. The next thing to find is the closed interval that contains the root. This is found by finding consecutive integers that causes the function to change sign from negative to positive or positive to negative, either one. It's hard to tell what that is just yet. Let's just start with an x value of 0, evaluate f of 0, and see where it's at. That will give 15 minus 2 times 0 minus 0 cubed, which will be 15 minus 2 times 0 is minus 0, minus 0 cubed is 0. 15 minus 0 minus another 0 is 15. Hard to tell what that says, but now we can evaluate the function at a consecutive integer, either to the left, like negative 1, or to the right, like positive 1. Let's evaluate it at positive 1 and see what happens. That'll give 15 minus 2 times 1 minus 1 cubed, which is 15. Minus 2 times 1 is a minus 2, minus 1 cubed, which is a 1. 15 minus 2 is a 13, minus 1 is a 12. And we have f of 0 is a 15. F of 1 is less positive. It's now a 12. It's trending in the correct direction. You want it to trend towards 0 by becoming less positive or less negative if it's on the negative side. So it's looking pretty good. Let's evaluate f of 2. That will give 15 minus 2 times 2 minus 2 cubed, which is 15. Minus 2 times 2 is a minus 4. Minus 2 cubed is an 8. 15 minus 4 is an 11. Minus 8 is a 3. It's now even less positive. It's headed towards maybe hitting the 0 and crossing over to becoming negative. Let's try f of 3. F of 3 will be 15 minus 2 times 3 minus 3 cubed, which is 15 minus 6, so minus 2 times 3, and then minus 27 for 3 cubed. 15 minus 6 is a 9, minus 27 is a negative 18. And it just changed sign from being a positive 3 to becoming a negative 18. And this occurred over the x-coordinates of 2 to 3. There is the interval we want to focus on. We can now write that interval for the condition on the intermediate value theorem. It needs to be continuous on the interval that is going to contain the root, and that's found to be 2 to 3. And since it's continuous on any interval, we can put in the closed interval 2 to 3 there, and it will hold true. The conclusion of the intermediate value theorem is f of x equals y for each y in the closed interval that is made up of the function evaluated at each of the endpoints of the interval where it changed, which is 2 to 3. The y-coordinates, we write the lesser one first, negative 18, the greater one second, 3, closed interval. For each y in that interval, at some x in the closed x interval, which is 2 to 3 here. What this is saying is that the function hits every single value between negative 18 and 3, including negative 18 and 3, at some x coordinate within the closed interval 2 to 3. So the function will hit every single value between negative 18 and 3, perhaps more than just that, but guaranteed at least it will hit every value between negative 18 and 3. One value that's between negative 18 and positive 3, between a negative number and a positive number, is the 0. So this shows that the function will equal 0 as one of its results at some x in that closed interval of 2 to 3. F of x equals 0 is the definition of what it means to be a root. Solving that for the x is the root of the function. And we know that this exists for some x in this interval. Therefore, another way of stating this is f of x has a root, and that root will be in the closed interval 2 to 3. So we've shown that it does have a root, and we have found the interval of consecutive integers that it lies within. The last thing to do is to show from up here that it has exactly one real root, and the intermediate value theorem does not show that. It only shows that it has a root and can find the interval of consecutive integers that it's contained within. To show that it has exactly one real root, we have to make use of the mean value theorem. To make use of it, we have to show that both conditions are met for it to apply. The first condition is the function has to be continuous on the closed interval. We have already shown that because that's the same condition needed for the intermediate value theorem. The second condition is on the derivative. So let's find the derivative of f of x, f prime of x. We will be taking the derivative of this f of x. The derivative, the first term is a constant with no x, derivative is 0. The second term is a constant with x, the derivative is the constant. Third term is a power rule, bring down the power, multiply it with the negative 1, subtract 1 from it. The derivative needs to be continuous, it's called differentiable, on the open interval. Well, minus 2 minus 3x squared is also a polynomial. And a polynomial is continuous on any interval, so this is continuous. It's called differentiable for the continuity of the derivative. Differentiable, and it's always on the open interval. Open because a function is never differentiable on its endpoints. Open indicated by the round brackets. It does not include the endpoints. But that condition is also met. So the function is continuous on the closed interval and differentiable on the open interval. Those are the two conditions needed. The mean value theorem does apply here. The conclusion of the mean value theorem says the slope of the tangent line evaluated at C will equal the slope of the secant line connecting the endpoints. Now the left side, f prime of c, can be evaluated by plugging c into f prime of x. That will give minus 2 minus 3c squared, and that will equal to f of b minus f of a divided by b minus a. Let's look a little closer at the derivative evaluated at c, the minus 2 minus 3c squared. And let's set it equal to 0 to see if it can be 0. Add 2 to both sides. Divide both sides by a negative 3, which will give negative 2/3. And then solve for c by taking the square root of both sides, which will give plus or minus the square root of negative 2/3. Since there's a negative under the square root, this is not a real number. and therefore there is no place where the derivative is 0. So we have the result that negative 2 minus 3c squared, the left side of the mean value theorem, can't be a 0. Therefore, the right side also cannot be a 0, because the two have to be able to equal each other. So this also cannot equal 0. Well, if that doesn't equal 0, then its numerator, which is f of b minus f of a, cannot be a 0, otherwise it will be equal to 0. Adding f of a to both sides, f of b cannot equal f of a. What that says is the function cannot equal itself at two different x-coordinates. So you cannot have the same y-coordinate for two different x-coordinates. So we've already showed that the y-coordinate can be 0, a root, for some x in the 2 to 3 interval. Well, if it equals 0 somewhere in there, it cannot equal 0 a second time. It cannot equal itself twice at two different x-coordinates. So this proves that there's exactly 1. And it's a real root because it's in the real number interval. But it does prove that there is exactly one real root, and that one real root is going to be found in the interval that's closed between 2 and 3. And there's exactly what we needed to prove here. So we have exactly one real root, and the interval of consecutive integers is 2 to 3.